So today we're going to begin studying Laplace transforms. And you may wonder why we're going to study Laplace transforms in the first place. Well, some of you are engineering students or physics students, and you've studied LRC circuits and problems like this. So the interesting thing about Laplace transforms is that we can deal with interesting functions. For example, this forcing function E of t here for voltage in the LRC circuit differential equation. Where we just have a first order differential equation. L is inductance, R is resistance, I of t represents the current, and the derivative of I with respect to t represents the charge. Now, I don't want you to focus that much on the actual application, but what if we had a voltage function that wasn't one of our nice functions, like a sine or cosine? What if it was defined as a periodic function, like this picture that I have here? So let's say these are defined in seconds the time. What if from 0 to 1 second the voltage was 1, then from 1 to 2 it was 0, then from 2 to 3 it was back to being 1, from 3 to 4 it was 0, and it just kept continuing like this. Now up to this point we really wouldn't have a way to do this problem other than very complicated procedures. So that's why we study Laplace transforms. So they're really useful when you're solving ordinary differential equations, when you have these types of functions. So if you have studied these types of situations before, you may have studied something called a unit step function, periodic functions, and impulse functions. So all three of these types of functions come up when you're studying applications like this, and Laplace transforms are really helpful in solving those problems. So let's look at what a Laplace transform is. So here's the definition of a Laplace transform. So let's suppose we have a function f of t that's defined on the interval from 0 to infinity. The Laplace transform of f of t is a function of s defined by this integral. So this f of s represents the Laplace transform of the function little f, and it's defined by this integral. It's an improper integral from 0 to infinity of e to the minus st times f of t, the given function, dt. So that's provided that this improper integral exists. So let's just take a minute to review what it means to be an improper integral and how do we evaluate an improper integral. So let's take a look at this example. Let's have the integral from 0 to infinity of the function e to the minus t dt. Now we're not doing a Laplace transform right now, I'm just doing an improper integral to remind you of how to evaluate it. So you remember that you can think of integrals, usually definite integrals, but we can think of all integrals as an area problem. So think about this as the area under the curve of the function e to the minus t from 0 to infinity. So I tried to draw a little sketch over here to the right. So this is supposed to be the curve e to the minus t. I've just kind of defined what the area looks like. And so how do we go about evaluating that problem? Well, we think about it as an integral from, say, 0 to some finite number. We'll call it capital M. We'll do the definite integral from 0 to m of our function and take the limit as m approaches infinity. So that's how you convert this improper integral into an integral that we can evaluate. So we're really just going to use the fundamental theorem of calculus. So the antiderivative of e to the minus t is the negative of e to the minus t, and we're going to evaluate it from 0 to m when we plug in. And before I do that, if I have a negative sign here, I like to pull out that negative sign out in front so I don't worry about it until the end. So when I evaluate at my limits, I have e to the minus m. Remember, I'm plugging in these values for t. I'm integrating with respect to t. So I have m, e to the minus m. I plug in 0 minus e to the 0. Now we know e to the 0 is 1. And what happens to e to the minus m as m approaches infinity? Well, it will go to 0, right? The graph of that gets smaller and smaller, the y value. So this approaches 0. So when we take this limit, we have the negative, because the negative sign's out in front, This is 0 minus 1. Multiply -1 times -1, we get 1. So the value of this improper integral is 1. And see, the limit existed. That's what we mean up here when we say provided the improper integral exists. When we get a finite number, it exists. So let's calculate the Laplace transform of a really simple function, f of t equals 1. So by the definition, the Laplace transform of the function 1 is this improper integral. By definition, you have the e to the minus st function there. F of t is 1. So we're just evaluating the improper integral of e to the minus st dt. And we're integrating with respect to t. So that s is like a constant. Now just remember from calculus, the integral of e to the kt, its antiderivative is e to the kt over k. So here, in our problem, the k is like negative s. So when we integrate it, we get e to the minus st divided by negative s. And my favorite trick is to pull that minus 1 over s out in front, evaluate at the limits of integration. So we'd have e to the minus s times m, and then minus e to the 0. Again, as long as that s is positive, e to the minus sm goes to 0, e to the 0 is 1. So in here we just have 0 minus 1, which is negative 1. Multiplying by the minus 1 over s out in front gives 1 over s, as long as s is positive. So the Laplace transform of the function 1 is just 1 over s. See, this is that function of s we were talking about. So anytime you take a Laplace transform of a function, it comes out to be a function of s. Let's do one more. This is another common one. And then I'll teach you how to take some of the common ones and build on that without using the definition. So what if we try to find the Laplace transform of the function e to the at, where a is just some constant? Again, we're using the definition, so we replace f of t with e to the at. Now we have two exponential functions. We can add the exponents, and let's say I want to factor out the negative t. That would leave you with s minus a in parentheses. So that's in minus t times s. That would be a plus at. So we've done that correctly. Just like in the last problem, this s minus a, just think about that as a constant, minus s minus a. So when we integrate it, again, we're taking the limit, changing this to a definite integral, 0 to m, take the limit as m approaches infinity. Now the k in our antiderivative formula is minus s minus a. So we find the antiderivative is just e to the k divided by k. So here, e to the minus kt over minus k, just like we did before. Now, my favorite thing to do, factor out this 1 over minus s minus a, put it out in front. Then plug in your limits of integration. So we have an m here. We're plugging in for m because we're integrating with respect to t. So we have this expression, minus e to the 0. E to the 0 is still 1. Now, as long as s minus a is a positive number, to make this whole thing negative, that means s minus a is positive, meaning s is greater than a. As long as that's true, this part goes to 0. You have 0 minus 1, giving you negative 1 times that negative 1. So the Laplace transform of e to the at is just 1 over s minus a, where s is a number greater than a. So that's a formula. So we'll start to learn these over time. We won't have to keep applying the definition. Now I want you to know how to use the definition, but we will not be doing this over and over and over again. We will learn how to do these using tables of Laplace transforms and some properties. So don't think that this is all we're going to be doing for the next week. So we'll have some fun with this.